units of concentration, and delta HF. We've been talking about solutions and the importance of solutions and how to make solutions. This particular slide shows various types of solutions. As you know, solutions can be solids, they can be liquids, or they can be gases. So if you see this list, for example, air is a solution of nitrogen and oxygen. Antifreeze, brass, carbonated water, some kind of beverage, seawater, hydrogen and platinum. These are all types of solution, and you can see the state of the solution, the state of the solute, and the state of the solvent. And the thing to know is that in a solution, even though the particular members of the solution might have come from different phases of matter, when they're joined together, they actually take on the properties of the solvent, because remember, the solvent is the thing that's present in the greatest amount. If we want to talk about solutions, there's lots of different ways to talk about units of concentration. We've already talked about molarity, which is moles of solute per liters of solution. Then there are different ways to talk about those relationships between solute and solvent. We have mass percent, that's the mass of the solute over the mass of solution times 100. Mole fraction, and you can see the symbol for it, is the moles of that particular component divided by the total moles of solution, and that number will always be less than 1, by the way. And then molality, which is moles of solute per kilogram of solvent. Let's look at molarity first. Remember, molarity, capital M, is moles of solute per liter of solution. This was discussed in an earlier chapter, so it should be pretty easy. Here is an example. Consider separate solutions of NaOH and KCl made by dissolving 100 grams of each solute in 250 milliliters of solution. Calculate the concentration of each solution in units of molarity. Well, this problem is pretty easy because obviously you just need moles of solute and you need liters of solvent. So if we have 100 grams of each, they're going to be different because, of course, the formula mass of sodium hydroxide is different from that of KCl. And so you would first take the sodium hydroxide, let's say, and that's 40 grams per mole by looking up sodium and hydroxide. And KCl has a formula mass of 74 grams per mole. You would then convert both of those to moles. So we have 100 grams of, let's say, NaCl, and you go from grams of NaCl to moles using the 40 and get a number, and then whatever number you get, you're going to divide by 0.250 liters. And that will get you the molarity of sodium hydroxide. You're going to do the same exact thing with potassium chloride, but of course you're going to be dividing by 74 this time. When you calculate both, you get the answer, which is 10 molar sodium hydroxide and 5.37 molar potassium chloride. So that is a review of molarity. Now, another unit of concentration to look at the ratio between solute and solvent is mass percent. Pretty easy to remember because mass reminds us that we want to have grams or kilograms. And for mass percent, you're going to take the mass of the solute divided by the mass of solution times 100. So here's an example of a question you might see. What is the mass percent by mass concentration of glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water? All right, mass percent, remember, is mass of solute over mass of solution. We don't even need to worry about glucose and its symbols and its formula mass because we're going to take 5.5 grams of the solute over 78.2 plus 5.5. Remember, the solution is solute and solvent, and when we work it out, we get 6.6%. And that's percent of glucose in that particular solution. Another way to find concentration is a unit called mole fraction. Mole fraction will become important in some calculations later. Mole fraction is the moles of the particular segment over the total. So it's like part over whole. So here is an example of mole fraction. A solution of phosphoric acid was made by dissolving 8 grams of H3PO4 in 100 milliliters of water. Calculate the mole fraction of H3PO4, and remember that the density of water is 1 gram per milliliter, which is very helpful, because with mole fraction, of course, you need to get to moles. And with knowing 1 gram per milliliter, that essentially means this is 100 grams of water. So we would have to convert both of these to moles. So I would look up the formula mass for H3PO4, and I believe when I did that I got 98. So this is 98 grams per mole. Oh. And of course water has a formula mass of 18 grams per mole. I'd convert them both to moles, and when I did, I actually got, for phosphoric acid, I got 0.0816 moles of H3PO4. I would then convert water, and I got 5.556 moles of water. When I did the calculation, what I would do is I would put 0.0816 moles over the sum of 5.56 and 0.0816, because it's of the total moles of solution. So 5.637 moles. When I work it all out, I get 0.0145 as the mole fraction. And then one of the last units of concentration in this particular chapter is molality. Remember, molality is moles of solute divided by kilograms of solvent. We've used this unit before in Intro Chem. Molality is a great unit because it does not depend on temperature. Moles and kilograms remain constant no matter what the temperature, and that's why eventually we will use it for freezing point and boiling point. So molality, or lowercase m, is a great unit. Here is a example of a molality question. A solution of phosphoric acid was made by dissolving 8 grams of H3PO4 in 100 milliliters of water, just like before in the previous example. Calculate the molality of the solution, again assuming water has a density of 1. Alright, so we need moles per kilogram. Now, from the earlier question, I already calculated moles, which for H3PO4 was 0.0816. And we need the kilograms. Now we know that it was 100 grams of water, and unlike before, I don't need to convert to moles. I just need to convert to kilograms, which is 0.1. And of course, when I work it out, I get 0.816 molal, and that's the concentration of that particular solution. Now, energies of solution formation, or delta H, heat of solution. We called it delta H. The enthalpy change is associated with the formation of the solution. It's the sum of the delta H values for the steps. In other words, if we know the delta H of one step and the delta H of the second step and the delta H of the third step, we can actually just add those delta H's up to figure out the delta H of the entire reaction. I think we used to call this Hess's law. Delta H solution may have a positive energy or a negative energy, or negative sign. Delta H positive and delta H negative. Remember, delta H negative is an exothermic reaction, and that's favorable. That's a natural direction of change is more likely to have energy released than energy absorbed. Delta H positive is one where energy is taken in. You're adding energy to the reaction. So here are two pictures. This should look somewhat familiar to you, although before, I think what we did was we had energy over there and we actually just had another axis down here. Whoops, that's a little crazy. These are the reactants, and these are the products. And then we had kind of, well, something that kind of looked like that, or activation energy. I know we decoded these reactions before. Here, this kind of might look more familiar. Oops, except for that last part, because it looked like I did not draw it properly. There we go, sort of. And again, these are the reactants, and these are the products. And you can notice that this reaction starts with a lot of energy and ends with less. Remember, this is the exothermic reaction. The endothermic is letter B. The reactants have a certain amount of energy, and then its energy is then taken into the reaction, and the reaction ends with more energy. What they're showing here is simply that the reaction is the sum of those two energies. But it helps us remember, in this case, that delta H, which is difference, the products minus the reactants, is going to be a negative number. Because whatever energy this is going to be less than this one, and when we subtract products minus reactants, your value will be a negative number. And of course, in the second graph, you do look at delta H, and you say delta H are the products minus delta H are the reactants. Here's the products up here, here's the reactants down here. When we subtract the two, we're going to get a positive delta H value. So that's just a reminder of something we've already done. So here's a good question. Explain why water and oil, a long-chain hydrocarbon, do not mix. In your explanation, be sure to address how delta H plays a role. Well, you might remember that like dissolves like. And that is a concept that we had in intro. And that essentially means things that are similar in structure will dissolve in one another, and things that are dissimilar will not. So something that's polar will dissolve in something else that's polar. Something that is nonpolar will dissolve in something else that's nonpolar, but polar and nonpolar will not mix. So that's probably my first explanation. But it says here you want to make sure to address how delta H plays a role. So heat of reaction. Perhaps the delta H value, you could never get enough energy for that reaction to take place. Maybe you don't have enough energy to go from the reactants to the products. You can't reach the activated complex. You can't have an intermediate that allows for products to be produced. So that might be one explanation about how delta H plays a role. The delta H value is relating. So in general, in terms of delta H, one factor that favors the progress is an increase in probability that the state when the solute and the solvent are mixed. So if we are changing in such a way that we are producing something more favorable, the reaction is going to happen. Processes that require large amounts of energy tend not to occur. So perhaps when you're mixing oil and water, it takes so much energy, it doesn't allow for the thing to happen because it takes so much energy to overcome that intermolecular force. And again, like dissolves like.